Alright, so last time we were talking about acceleration. We've also talked about the motion graphs. Now we're going to talk about what happens when we have an object that is accelerating at a constant rate. So when we say uniformly accelerated motion, what we mean by that is that the acceleration is going to be constant. So you can get a lot of information from motion problems when you have a constant acceleration. So when I have a constant acceleration, and I'm looking at my VT graph like this, remember that on a VT graph, acceleration is the slope. So if I have a linear line on a VT graph, that would represent constant acceleration, because you know on a linear line the point should be the same at every single point, or the slope should be the same at every single point. So the slope is equal to acceleration, the slope is equal at every single point here, so acceleration will be the same. So here, this is what the VT graph would look like if we had constant acceleration. If I did not have constant acceleration, meaning on the VT graph, the slope would not be the same at every single point, I would have a line that was curved. So I could have one going up, I could also have one going down, but anytime that we have a curved line here, the slope is not going to be the same at every single point. So we do not have a constant slope here, and I know that my slope is equal to my acceleration, so this is not constant acceleration. Now you also have another type of VT graph like this, and if you see this, this would be no acceleration. So no acceleration here because the velocity is staying the same. You also can see that your slope is going to be 0 here. Since your slope is 0, your acceleration is also going to be 0 here. So we're going to look at 4 new equations. So here are our new equations right here. VF is equal to VI plus AT, and then so on. We have 4 equations. We only knew 3 equations before this. So before this, the 3 equations that I knew would be velocity, which is the change in position divided by the change in time. I also knew speed, which is the distance divided by the change in time, or the time. And then I knew acceleration, which is the change in velocity divided by the change in time. These are the 3 equations we've already talked about. These are 4 new equations, and I will give you these on a test or quiz, but these will not be given to you, so you need to know these. So here are 4 equations. We need to look to see what variables we have in this case. So when I look at the equations, I have 5 different variables. I have VF, the final velocity. I have VI, the initial velocity. I have acceleration. I have T and delta T. Really, it's going to be the same thing, so time. And then I also have delta X, which is my change in position or displacement. So I have 5 variables. I have 4 equations. If I know 3 of the variables, I can solve for the other two variables. And that makes one happy physics student. Okay, so I have 5 variables, VF, VI, A, delta T, delta X. I have 4 equations. If I know 3 of my variables, I can solve for the other 2. So let's go ahead and look at some problems. So this question says, how long must a runway be for a plane to reach a takeoff velocity of 75 meters per second if it accelerates at 20 meters per second squared? So first thing, what am I looking for? So it says, how long must a runway be? So how long must a runway be would be delta x. That is my change in position. So I'm looking for that. Do not be fooled by the term how long. If it said how long does it take, that would be delta t. But it's giving me how long must a runway be, so that is how long is it, so that's a length, so that's going to be delta x. Now then it says a plane to reach a takeoff velocity of 75 meters per second. So I have a velocity of 75 meters per second, and now I need to decide if it's the initial velocity or the final velocity. So in this scenario, I have a plane and it's trying to reach this velocity. So since it's trying to get to this velocity of 75, that is my final velocity. So the plane is going on the runway, it's accelerating. You need to get to 75 meters per second to actually take off. And then it tells me that it accelerates at 20 meters per second. So my acceleration is 20 meters per second squared. So anytime that you see meters per second squared, that's an acceleration. So I need to know 3 variables. I only have 2 here. But in the problem, something is implied. It says, how long must a runway be for a plane to reach a takeoff velocity of 75? So the plane started from rest. Since it started from rest and then it's trying to accelerate to get to 75, the initial velocity is going to be 0 meters per second. This is something that is implied in the problem. So I'm given VF, A, and VI. So now I need to look to see which equation I will use. Pick the equation that only has one unknown variable. So you will not be able to use the same equation every time. You need to pick the equation that's going to work for your situation. So I would look to see which equations have delta x first, and then see if that equation only has delta x as the only unknown. So for example, let's look at the first equation right here. So VF, I have VF at 75. I have VI, that is 0. I also have the acceleration. And then I have time. Time is also unknown. But I'm not trying to solve for time, so I'm going to see if there's another equation that would work for me. I could solve for time here, though. So in the second equation, I'm looking for delta x. Right here, I have initial velocity of 0. Delta t is unknown. Since I have 2 unknowns in this equation, I cannot use a second equation. There are too many unknown variables. So looking at the third equation, I have VF, I have VI, I have acceleration, but I do not have delta x, but that's fine. That's what I'm looking for. So there's only one unknown in this equation. So I'm going to use the third equation. So VF squared is equal to VI squared plus 2a delta x. So now I only have one unknown variable, which is delta x. Everything else I have, so now I can just plug everything into the equation. So VF is 75. I'm going to square that. VI is 0. I'm going to square that as well. My acceleration is 20. And my delta x is unknown. So 75 squared will give me 5,625. That's equal to 0 plus 40 delta x. 2 times 20 is 40. So I can go ahead and just get rid of the 0 because it's not going to affect anything. So really what I do have is 5,625 is equal to 40 times delta x. So now in order to solve for delta x, remember you're going to do the opposite of whatever's being done. Divide both sides by 40. So in this case, delta x will equal 5,625 divided by 40. I will get 140.625 meters. That's my answer. So when you do these problems, the first thing you do is translate the problem. So figure out what variable you're solving for and also figure out what information the problem gives you. Then you're going to pick the equation. So you're going to pick the equation that will work best for your situation. So make sure it only has one unknown variable and then plug and solve. Okay. All right, let's do another one. Alright, so my tea tumbler falls off my car and slides along 95 South for 75 meters. Friction slows my tumbler at 6 meters per second squared. How fast was the car moving when the tumbler fell? And then also, how long did it take the tumbler to stop? So, first thing I'm going to do, I'm going to translate. So it's asking for how fast was the car moving when the tumbler fell. So fast would be some velocity. So are we looking for the initial velocity or the final? Well, right here it says my tea tumbler falls off my car, slides along 95 South, and slows my tumbler, and this should be to rest. It should say that in the problem. So it's going to slow it down to rest. So if I'm going to rest, that would have to be my final velocity there. So I'm looking for what velocity my tumbler started moving at. It also says how long did it take. That's going to be delta t. We also do not know that. So what information are we given here? If I'm going to rest, my final velocity will be 0. And then it also tells me that my tea tumbler slides along 95 South for 75 meters. So my delta x is going to be 75 meters. And then it tells me my acceleration is 6 meters per second squared. Okay, so right here it tells me that my acceleration is slowing down, so we're going to assign this as a negative acceleration. So now we're going to pick a good equation to solve for this. So let's look for an equation where there's only one unknown variable. So I have VF, I have delta x, and I also have acceleration. So looking at this, I have VF, I do not have VI, I have the acceleration, but I don't have the time, so I cannot use the first one. There's too many unknowns. So the second one, I have delta x, I have delta x. I do not have the initial velocity, nor do I have the time, so I cannot use the second one. So this is out, this is out. Looking at this one, I have VF, I do not have VI, so that's one unknown. I have the acceleration, and I also have delta x, so I can use the third equation again. So now I can just plug everything in. So VF is going to be 0. I'm going to square that. VI is unknown. Acceleration is going to be -6. Delta x is going to be 75. So simplify. 0 is equal to VI squared plus negative 2 times 6 times 75 should give me 900. Okay, so now to solve this, I need to get rid of everything that does not have the variable. So VI squared, we're going to leave that alone for now. Get rid of everything else. Since we're subtracting 9 here, it's negative, so we're subtracting it. We're going to add 900 to both sides. That's going to go away, so 900 is equal to VI squared. So now to get rid of the squared here, we're going to do the square root. So the square root will cancel the squared. So VI is equal to 30 meters per second. So that's the first part. So now I have VI, and now it's still asking for delta T. Now we're going to solve for our time. So we should be able to use almost any equation for this. So looking at the first equation, I have VF, I have VI, I have acceleration, and I'm looking for time. So I can use the first equation here. AT. So VF is equal to 0. VI is equal to 30. Acceleration is going to be -6. The time is unknown. So now I have 0 is equal to 30 plus -6t. So now I'm going to get rid of everything that does not have the t. So I'm going to subtract 30 from both sides. Remember, I do the opposite. So it's -30 is equal to -6t. So now to get the time, I'm going to divide both sides by -6. So t is equal to 5, and that should be seconds. Okay, so let's look at a few other problems. I picked some different problems. Okay, so let's do this one first. So if you have your note packet, you might want to just write this down. I'm not sure that this one is in there. I just want to make sure we cover all different types of problems here. So a car starts from rest and accelerates uniformly to reach a speed of 21 meters per second in 7 seconds. What was the speed of the object after 2 seconds? Okay, first of all, do not get confused by the word speed here. Because remember, speed and velocity can be the same if you're going in a straight line. So when it starts talking about speed versus velocity, if it's moving in a straight line, the speed is equal to the velocity. So when we're looking at this question, it says, what was the speed, so that's going to be a velocity, of the object after 2 seconds? So that will be a final velocity. So after 2 seconds, how fast was the car going? Okay. So we want to know the speed at 2 seconds. So our change in t, or time, will be 2 seconds. It also gives us more information here. It tells us that the car starts from rest, so your VI is going to be 0. Because it starts from rest, and then it accelerates uniformly to reach a speed of 21 meters per second. So we have 21 meters per second, and that's also a velocity. And we're going to consider that a final velocity because it reached that speed. And then it did that in 7 seconds. So what we have to do is we have to solve for the velocity at 2 seconds, not 7 seconds, because it gives us the velocity for that. We also know that to get to this speed, it started at 0. So right here, if I'm looking on this side, I have a delta t, I have vi, but I do not have enough information yet to get the velocity at this time. But I do know that the car accelerates uniformly. That means A is the same throughout the entire trip. So acceleration is the same throughout the entire movement of the car. So what we can do is we can solve for acceleration here because acceleration should be equal at 2 seconds. So we need to solve for acceleration first. And sometimes you will have problems where you actually have to solve for one variable to get another. So this one is a little bit trickier. So now, again, we're going to pick an equation that will work best for us. So for the first one, I have VF, I have VI, I have delta t, and I'm looking for A. So this one is perfect because I only have one unknown variable. So my VF right here is going to be 21. My VI is 0. My acceleration is unknown. And then my time is 7 seconds. So let's go ahead and get rid of the 0 because it does not impact my problem. Adding 0, subtracting 0 will not impact anything. So it's 21 is equal to A7 or 7A. So now to get acceleration by itself, I'm going to divide both sides by 7. So my acceleration in this case is 3 meters per second squared. So remember, your acceleration is going to be the same because it says it accelerates uniformly throughout this movement. So my acceleration over here is also equal to 3 meters per second squared. Now I have 3 variables. I can solve for this one. So looking at the first equation, I have A, I have T, and I have VI, so I can just, again, use this equation. So VF is unknown, VI is 0, acceleration is 3, and delta T is time. Okay, so now VF is equal to 0 plus 6, so VF is equal to 6 meters per second. So remember, in this problem, acceleration is going to be the same, but velocity will change throughout the problem. So at different moments in time, your velocity is going to keep changing. In this case, it's going to keep increasing. Okay, so let's look at another problem.